Okay, so um, hopefully the exam went well. I saw that pretty much everybody had submitted something, so that's good. So anyway, uh, the exam will be graded well at some point in the next week and a half, 2 weeks or so. Um, So I'll post solutions to the exam um, in I'll say next week. So at the end of next week I'll post or maybe next Wednesday I'll post solutions. So don't refrain from talking about the exam till I post solutions. Because due to time zones and a lot of people having to a lot of international students having to go home and stuff. There's still some issues for a couple of hours. I still may have like a couple of exams slowly trickling in due to those kind of things. But other than that, it looks like I think literally everybody had already submitted the exam. But still, just to be cautious, don't refrain from talking about the exam. For now until I post solutions. So I'll post solutions, like I said, like next Wednesday or so, and then the non-disclosure agreement will be lifted, and you can talk about it all you want to. So anyway, now you've seen how that's going to go. The final exam will be more of that. It'll just be cumulative, so it will contain basically a problem from every section that we've done so far. So anyway, on to something totally different, and that is linear systems. So the idea here, we're totally leaving behind the world of first and second order single differential equations, and we're only talking about linear systems here. And even though the notes goes through the theory of linear systems of differential equations that involve some non-constant coefficients in general, or even just something more general than this thing. For us, practical purposes, when we say a linear system, we're going to mean a linear system like this. So what does this mean? So my x sub 1 of t and x sub 2 of t are unknown functions. Okay, so and these unknown functions satisfy this system of differential equations. It's called a linear system. You'll see why in a second, other than being a system of two first-order linear differential equations. So the other thing I should say here is, I think I forgot to mention in the intro, is that all of these systems we consider are going to be first-order. So these are first-order systems, meaning that the highest derivative showing up here is a first derivative. Okay, so that's exclusively what we're going to be concerned with in Chapter 3. So we have two unknown functions, x sub 1 and x sub 2, that we seek. And these quantities a, b, c, and d are constants. So these are real constants, so all of them are just some real numbers. Okay, and so our linear systems that we're going to be talking about look like this. So think about this for a second. I have two unknown functions, x sub 1 and x sub 2. And so I am saying that my two unknown functions satisfy the system of differential equations. The first derivative of x sub 1 is a times x sub 1 plus b x sub 2. And the second derivative, the first derivative of x sub 2 is cx sub 1 plus dx sub 2. And so these, because this is a system, these are meant, when I write this, I'm saying that these are satisfied simultaneously. Okay, and so I seek a solution to this system. Okay. Well, what does a solution to this system mean? Just like for linear systems, not of differential equations, but just go back to pre-algebra, right? What was a system of linear equations like when you were studying, pre-algebra or algebra 1 stuff? Well, the system of linear equations was just a set of linear equations that had to be satisfied simultaneously, so that a solution to that system satisfied every equation in the system simultaneously. So seeking a solution to this system, i.e., I wish to find the two unknown functions, x sub 1 and x sub 2, satisfying, call this star. Okay. Now, there's a whole host of questions that I can already, or that you might already have, which is, well, if I asked you how many solutions exist to some given differential equation, not a system now, just a given differential equation, the answer is infinitely many, right? So typically the general solution, right, involves arbitrary constants that parameterize the family of solutions, right? So, and that was true even of first orders that we did in chapter 1. And if you wanted to nail down a particular unique solution among that family, you had to specify some initial condition. So the same thing is true here. So same thing is true here. So let's rewrite my system. So my system is dx sub 1 dt is a times x sub 1 plus b times x sub 2, and dx sub 2 dt is c x sub 1 plus d x sub 2. Okay, so here's my system, and maybe I consider an IVP, right? So there's an initial condition. My initial condition needs to be an initial condition for both x sub 1 and x sub 2. Right, so maybe x sub 1 of 0. This doesn't need to be 0, but frequently we know that it is. So x sub 1 of 0 is equal to some value, and x sub 2 of 0 is equal to some other value. Right? So I can formulate an IVP in this way by specifying an initial condition. Okay. So, before I go any further, I'm going to warn you that the way that I go through this material is going to jump around a bit in the notes. So, warning, I'm going to jump around a bit. Relative to the notes. Okay, so that the bit that I do first is actually part 5. Okay, so essentially I am going to start at 3.5. So essentially I'm going to start at 3.5. Do a little prior to 3.5 and then move on. Okay, so there's a reason for this. One, because of the truncated schedule, some of the theory stuff that's developed in the early part of chapter 3 is just not going to be as important to us. And it's going to be a lot quicker for us to deal with this after we have 3.5 taken care of. So the reason why 3.5 in particular is 3.5 is the thing that gives a recipe for solving these things. Okay, so everything prior to 3.5 gives some more general theoretical framework that works. But as far as a practical step-by-step deterministic process that allows you to solve these things, 3.5 is what contains that. And so that's where I'm going to start. Now, I lied a little bit because actually, before I can do any of this, I have to talk about linear algebra. But before I can do any of this, I must spend a decent bit of time on linear algebra. Now, if you have had 240 or 461, then what comes next is going to be insanely boring for you, but also you're going to find this so laughably easy that, I don't want to encourage you to take time off or anything, but that's what you're going to feel like doing, because if you know 240, if you did well in 240 and you understood the material in 240, then this bit of material is going to be extremely easy for you. So those of you that have not had 240, and I know that that's a good chunk of people, worry not. Basically, you can rest assured that that I'm going to be going over everything that you need to know. So you don't need to. There's not too much you need to brush up on. I'm going to be glossing over some of the very, very basic stuff about matrices. So if you're rusty on any of that, you might want to brush up on that. So I will say that your discussion sections tomorrow, your TAs are going to go over a bunch of linear algebra review stuff, and so that's a good place. Same thing, any of the GSS sessions, I'm going to talk to them and make sure they're focusing on this linear algebra review stuff first, because if you have your linear algebra foundations, then what comes after is actually really easy, and is a bit of a canned recipe type thing. So really understanding the linear algebra is the most important bit. So why is the linear algebra important? Well, I called them linear systems, right? So maybe you think that linear algebra is important just from that hint, but there's a specific reason why the linear algebra comes in. Let's look at this equation and let's come up with a convenient way of writing this system. Okay, so I'm gonna rewrite it yet again. So here's my constant coefficient first order linear system. Okay, there's what it looks like. Now, it turns out that this is much easier to think about if I use matrices and vectors here. So this is more convenient using vectors and matrices. What do I mean by that? I can rewrite this equation. Okay, so I'm going to write, so here's some notation. I'm going to say I have a vector that depends on t, so it's a vector valued function. This vector is the vector containing my two unknown functions, x sub 1 and x sub 2. Okay, so x of t is the vector. It's a column vector containing those two entries, x sub 1 of t and x sub 2 of t. Okay, all right. So once I have this written, let big A be a 2 by 2 matrix. A, B, C, D. Before I go any further here, I'm going to do away with this for a second. Okay. So, recall, What does it mean to multiply two matrices? First of all, what does it mean to multiply a matrix by a vector? Let's say that A is the matrix A, B, C, D, 2 by 2, and X is the vector X sub 1, X sub 2. What is A times X? So this is the matrix A, B, C, D times the vector X sub 1, X sub 2. How does this work out? So you might remember how this goes. To multiply a matrix like this, you're thinking of a particular dot product of some rows transformed into columns and dotted with the columns of the matrix over here. So I'm not going to get into this. If you don't remember how to multiply matrices, you should brush up on that knowledge. So this is going to be recall how matrix multiplication works. So this is a 2 by 2 matrix multiplying a vector, which is really a 2 by 1 matrix. So the result is a 2 by 1 column vector. And that vector is AX1 plus BX2 in the first slot. And in the second slot, it's CX1 plus DX sub 2. Okay. All right. And so, another thing to recall, if I have two vectors, U, that is a vector made up of a bunch of entries, U sub 1 through U sub n, and another vector, V, which is made up of entries V sub 1 through V sub n, then U is equal to V if and only if what is true? Two vectors are equal. You might remember this from Calc 3. Two vectors are equal if and only if all of their components, component-wise, are equal, right? So U sub 1 is equal to V sub 1, U sub 2 is equal to V sub 2, and so on, all the way down to U sub n is equal to V sub n. That's how you can say that two vectors are equal. Putting these things together, in light of this notation that I have introduced, note I can actually rewrite this system of equations. So what does this become? This becomes the system of equations dx dt is equal to a times x. Okay. Another way you might see this written is x prime is equal to ax. Okay. This is the notation we're going to be using throughout the rest of this chapter. Okay, so when you see notation like this, this is what we mean. We have a system of first order differential equations. We seek unknown functions x sub 1, x sub 2. We can think of, instead of looking for two functions that are our solutions to this system, we look for a single vector that solves this equation, dx dt is equal to ax, so that this single vector takes the role of our single solution that we're thinking of, right? And of course, I can, similarly, using this vector notation, if I had an IVP, I can specify some initial condition, right? If you like, x of some initial time is, x naught. Okay. All right. So that's how this goes. Okay. Now, question. Where does the linear algebra knowledge come in? So the answer is that it turns out that quantities associated with the matrix A determine the solutions to, again, we'll call this star. Well, okay, what I said there was basically nothing. Obviously, some quantities associated with A are going to determine the solution, since in this equation A is the only thing that's different here, right? I'm seeking solutions to this differential equation. X of 1 and X of 2 are unknown. I'm not given those. I'm trying to find them. So literally A, B, C, and D, those things are the only things changing, i.e. A, right? So from problem to problem, the only thing different in this equation is the entries of A. So what I said here was basically pointless and obvious from this. But what I really mean is that it's not just any quantities. It is linear algebra quantities that I can determine from A that are completely independent of this differential equation stuff, right? So the quantities in question depend only on matrix properties of A. Again, you might think that's obvious, but I just want to stress that the computations we're doing on A don't care anything about derivatives. Derivatives could not exist and it would still work out this way because this is purely a linear algebra thing. Okay. So this is the point. All right. And so specifically, the quantities associated with A that matter are its eigenvalues. Okay, eigenvalues and the associated eigenvectors. So if you know what eigenvalues and eigenvectors are, then you are in for an extremely easy time. If you don't know that, well, then that's what we're going to learn right now. Okay, so an aside, i.e., now for something seemingly completely different. Oh, I need a new pen, I think. I don't like that one. Okay, let's go over some basic stuff about matrices. I'm probably going to forget some stuff that you might not know, depending on your level of comfort with matrices in general, or matrices and vectors in general. So basic matrix vector stuff. If you need a refresher, the notes have a section. I believe it's 3.2. Let me make sure. No, it's 3.3. So chapter 3, section 3 in the online notes is good for review. Okay. So then before I get on to what is the most important thing, that is finding eigenvalues and eigenvectors, I have to talk about some basic matrix and vector stuff. And then we'll see how this plays into these equations. So basic matrix and vector stuff. First of all, the sum of vectors. Okay, so something simple. Let's say that I have two vectors, u and v, as before. And we'll say that those are vectors in Rn. That means I'm thinking of them as column vectors with n entries. So when I say this is what I mean. I'm thinking of these as column vectors with n entries. Now, it turns out that we are going to use, this should be v. So all of our examples we work out by hand are going to be, A is going to be 2 by 2. That's going to vastly reduce the amount of build-up that we need to do because 2 by 2 matrices are very simple. But I'm going to give you, whenever I think it won't hurt too badly. I'm going to give you a more general treatment of it because all of this stuff we're doing can be done for larger size matrices A. Okay, and so if I wanted to talk about U plus or minus V, right, to add or subtract vectors, in order for this to even be defined, these have to have the same number of entries. I can do this for matrices too, but it doesn't mean that much. So for two vectors, to add them or subtract them, you just do it component-wise, right? And so on. So that's how addition, subtraction of vectors works. You just do it in the entries. How to multiply a vector by a scalar. So if alpha is some scalar, that is some real number, then how do I talk about alpha times the vector u? Alpha times the vector u is just the vector I get where I multiply every single entry of u by alpha. So this is alpha u sub 1, alpha u sub 2, and so on, all the way down to alpha u sub n. Okay. All right. So here's some basic vector. This is very, very basic vector arithmetic that can be done. Now, do I actually need to talk about dot products or not? I don't think so. I don't think I need to talk about dot products really. I think that if you understand basically how to add vectors and multiply vectors by constants in this way, I'm pretty much primed to be able to immediately talk about eigenvalues and eigenvectors. Now, this isn't a linear algebra class, so I'm not going to be going too hard on my descriptions, or I'm not going to fully describe to you why it is that eigenvalues are so important or what it is they're even trying to say. But I'll just give the very, very basic stuff. Although what will come later should kind of serve as an illustration of why eigenvalues are important. So, the most important thing in Chapter 3. So recall, in Chapter 2, I said you had to understand how to construct the homogeneous part of a solution, because literally every single thing that you were asked to do would use that. Secondly, in finding the particular solution, right, you had to, like if you were, for a non-homogeneous problem, I mean, if you were constructing a particular solution, using key identities, undetermined coefficients, you had to know the characteristic, the degree, the multiplicity. You had to know those things because every single problem used those. So similarly here, every single problem that is going to ask you something in Chapter 3 is going to require you to do this. Okay, and so the most important thing in Chapter 3 is to compute all eigenvalues and eigenvectors associated to a given matrix A. Okay. This is by far the most important thing that you can do. And in fact, if you understand absolutely nothing about the intuition of what's going on as far as the differential equation is concerned, understanding nothing but knowing how to do this will get you a huge part of the way to being done, even if you really don't understand anything that's going on. This is by far the most important thing in all of Chapter 3. Being able to do this is required to solve any problem. Okay, so computing eigenvalues and eigenvectors associated to a given matrix A. Eigen here is is German, meaning like particular. What are the eigenvalues and eigenvectors associated to matrix A? I'm going to do the definition real quick, and then I'm going to talk about how to find them. And so, again, it's not a linear algebra course, so I'm not going to go through the whole theoretical understanding. But the idea behind an eigenvalue is that, and an eigenvector, is that multiplying by a matrix is, while doable, it's crappier than multiplying by constant. Okay, so taking a vector and multiplying it by a matrix is worse or harder than taking a vector and multiplying it by a constant. So we saw, you take vector, you multiply it by a constant, well, that's easy. You just multiply every single entry by that constant and you're good to go. But if you take matrix and multiply it by a vector, well, I mean, it's not really super complicated, but it's more complicated than just multiplying by a single constant. Okay, so it turns out that it is of particular interest to us when multiplying by a matrix behaves like multiplying by a constant. And so, the definition of eigenvalues and eigenvectors, and you can't have one without the other. When you talk about eigenvalues and eigenvectors, as we shall see, they do not exist in a vacuum. As you talk about an eigenvector, you cannot help but mention an eigenvalue and vice versa. Okay, well, that's mostly true, okay, especially when you talk about eigenvectors. But anyway, so let A be an n by n real matrix. I know that this says let A real matrix. That sounds stupid, but I'm not going to rewrite that. So a number lambda is said to be an eigenvalue of A if there exists some vector v such that A times v is equal to lambda times v. Before I talk about what this means, I'll say in this case, v is said to be an eigenvector for A associated to the eigenvalue lambda. And together, they constitute an eigenpair of A. We'll call it lambda v. That is an eigenpair. Okay, so now I'm going to stop for a second and talk about very briefly what this is saying. So as I said aloud in words before I wrote this down, a number lambda is said to be an eigenvalue of A if there exists some vector v such that AV is equal to lambda v. What I was saying is that we wanted to know when multiplying by a matrix acted like multiplying by a real number. Okay, or a complex number. I should stress here, actually, I definitely do not want to say real number here, because I said a number lambda. It turns out that we are being very squishy here, and we will even allow complex numbers here. Now you might say, wait, complex numbers? How do you multiply by a complex scalar? Well, it turns out, going back here, if alpha is changed now to not just be a real number, but to be a complex number, the same thing is true. So I can treat it in exactly the same way. I multiply it by a complex number in the same way that I normally do. All these use of one, since U's and V's, these U's and V's have real entries, so this is just complex times real number all the way down. It's easy to do. So yeah, it's no problem at all for this thing to be a complex number. Okay, so the idea is that I'm looking at when the matrix A is, or multiplying by the matrix A is the same as multiplying by a real or complex number, lambda. Okay, and the answer to that question is, well, it is exactly the same on these eigenvectors, where the lambda in question is the eigenvalue, and the vector, such that multiplication of A with that vector yields this multiplication by lambda, that number, that is the eigenvector. The lambda is the eigenvalue. Together they form a pair, eigenvalue, eigenvector, lambda v. That's called an eigenpair. Okay, so again, theoretically, you don't need to understand, like, intuitively what an eigenvalue eigenvector pair is doing. You just need to know how to find them. Okay, so first, a couple of facts. So before I discuss how to find them, here's a fact. Oh, that's not where the apostrophe goes. Here's a fact. So, fact. If lambda v is an eigenpair of A, then lambda alpha v is also an eigenpair of A, where alpha is a real or complex scalar. So this immediately answers the question of whether or not an eigenpair is unique in some way. The answer is no. If I have an eigenpair, I can scale the vector in question by any scalar I like and get another eigenpair associated with the same eigenvalue. So no, they're not unique in that sense, but up to this multiplication by a scalar, they are. Okay, this will come into play. This will come into play later. All right. So here's the first of many facts that we're going to talk about when it comes to these things. So this is a very nice thing to know, that if you have found an eigenpair, you can get another eigenpair just by scaling v. Okay, even though it's again, just some other eigenpair, we'll see that there is still a way to list all of the eigenpairs. Okay, so this is just covering our bases when I mention all the eigenpairs, and you say, oh wait, you didn't account for multiplying this thing by 2 or something, right? We're just going to include that in the same class. Okay, so big question. How do I compute eigenvalues and eigenvectors? For a given matrix A, obviously. So this is going to be done in 2 ways. So I have 2 steps. One is a step involving the characteristic polynomial. This has been very carefully defined so that we are using the same words here because it is the same thing in a proper context, okay? So this characteristic polynomial is not the same as the characteristic polynomial that that you dealt with in section 2, in chapter 2, but it is the same thing. But on its face, it doesn't look like it's the same thing. So there's 2 steps. Characteristic polynomial of A. This finds eigenvalues lambda, and 2, Cayley-Hamilton Theorem. This only works for 2x2s, but for us, that's good enough. If you have a matrix that is bigger than a 2x2, you can do this step with a method of solving a linear system that if you are coming from 240 or 461 and you already, or coming from anywhere, if you already know about eigenvalues, eigenvectors, you have likely done something else other than Cayley-Hamilton. So if you know how to solve for eigenvectors without using Cayley-Hamilton, you are free to do that to your heart's content. I don't care. This is just the way that I'm going to cover how to do it here because I don't have to solve any linear systems here. So Cayley-Hamilton, and this finds eigenvectors associated to lambda. Okay. So those are my 2 steps. Okay. Okay, so first step, characteristic polynomial. What is the characteristic polynomial? Let A be an n by n matrix. The characteristic polynomial of A is P sub A of Z, which is written to be the determinant of Zi minus A. Now, I'm not going to go over why this is the thing that does it. Maybe I will maybe I should very quickly talk about this. So if I go back to this equation here, AV minus lambda V, I can rewrite this as an equivalent equation A minus, or I guess I should do it in the other direction if I'm gonna write it like that. So I'm going to do this as lambda I minus A times V is equal to 0, the 0 vector. Right? So 0 vector is just a vector containing all zeros. Here I have lambda I minus A. I is the n by n identity matrix. And I have to have this I here. Lambda minus A doesn't make any sense because lambda is a scalar and A is a matrix. And if you're going to add or subtract matrices, they have to be the exact same size. So if A is n by n, I have to have an n by n matrix here. So it makes sense to have I here. So this is what I get. I have this equation here. And so looking for a solution, say V, to this equation for some lambda value is equivalent to wanting a non-trivial solution to this. So when I say non-trivial, I mean not the 0 vector. By convention, we are going to consider the 0 vector to never be an eigenvector, okay, for some eigenvalue. We're not going to talk about it, I'll say. And so in that way, I seek a non-trivial vector V that solves this. But if I want this to have a non-trivial solution, by linear algebra, what has to be true is that the matrix I'm multiplying here has to have determinant equal to 0. I'll go over later what determinant is. We've already talked about determinant, at least of 2x2s before, and you should know what a determinant of a 2x2 or 3x3 matrix is, or how to compute them by now. But I'll go over that again in case you have forgotten. And so the characteristic polynomial is the thing that I get when I take the determinant of that quantity. Now, I've already spoiled the fun a little bit when I wrote this equation out because I said I want the determinant of this thing to be 0. And so it turns out that the roots of this polynomial are what really matter. Okay, so a couple of facts about this. So fact 1. P sub A of Z has degree n. So if A is an n by n matrix, this characteristic polynomial has degree n. Okay. Second fact, this is by far the most important fact. I probably shouldn't list it as like a sub fact, so I'll put this is a 3-star fact. The roots of the characteristic polynomial are the eigenvalues of A. So this cannot possibly be stressed enough, because now I have just given you a way of computing eigenvalues for A. I write out what this stupid polynomial is, and then I find all of its roots. Well, that's kind of annoying. Why are we using z instead of lambda? To show that this is a polynomial, so it takes any value z. The roots, when we're talking about the roots, we'll use lambda because it's the roots that are the eigenvalues. And I only want to use lambda when I'm talking about eigenvalues. Okay. Oh, don't worry about any e to the z stuff yet. You'll see that later. You'll see how all this stuff is actually the same. Okay, so the roots of the eigenvalues, the roots of the characteristic polynomial are the eigenvalues of the matrix. Okay, but there's a problem here, right? That's great and all, but finding the roots of some 17-degree polynomial is terrible, right? Finding the roots of even a degree 5 polynomial can be terrible. So, if the degree of this thing is large, then there's still a lot of work to do here. This could be really nasty. But it turns out if A is a 2x2 matrix, then there's a particularly nice expression for the characteristic polynomial. And that expression is the following, and you should remember this. Then the characteristic polynomial is going to be z squared minus the trace of A times z plus the determinant of A. This is a handy little formula. I even use this to come up with examples when I'm teaching 240 or 461. While I'm standing at the board, if I want a matrix to have a particular characteristic polynomial, this is what I do in my head. So what are these quantities? So if A is a 2x2 matrix, let's write over here that A is the matrix A, B, C, D. Okay. Then the trace of A. The trace of a matrix is the sum of its diagonal entries. Okay. So the trace of a matrix A is A plus D. This is a 2x2 matrix here. But trace is a thing that's defined for larger matrices. So if A was a 3x3 matrix, it would be the sum of the 3 entries along the diagonal. And so what is the determinant of A? Well, you already know that. So determinant of A is AD minus BC. And so knowing these two quantities associated to a 2x2 matrix A, this is what my characteristic polynomial is. Okay, so this is a lot more manageable. I mean, and since A is a 2x2, this is just a quadratic. So at absolute worst case scenario, I can use the quadratic formula and be done. So let's do a couple of examples of computing this. And so after I do these examples, I'll talk about how I can use this to find eigenvectors. So example, let A be the matrix, symmetric matrix 3, 2, 2, 3. Find all eigenvalues of A. Okay. So how do I find all eigenvalues of A here? So the characteristic polynomial of A is P sub A of Z, which is Z squared minus the trace of A, Z, plus the determinant of A. So let's compute the trace of A. So the trace of A is 3 plus 3, which is 6. And the determinant of A is 3 times 3, which is 9, minus 2 times 2, which is 4. So 9 minus 4 is 5. And so this is Z squared minus 6Z plus 5. Okay. Turns out this factors very nicely. So this is Z minus 1, Z minus 5. So the eigenvalues of A are the roots of the characteristic polynomial. So lambda equals 1 and 5 are the eigenvalues of A. Okay. Now, this raises a couple of questions. One, how many eigenvalues can a matrix have? So before I can answer that, let's just talk about what the eigenvalues are. We've already seen that the roots of the characteristic polynomial for a matrix are the eigenvalues of A. Let's use some algebra knowledge here. If the characteristic polynomial of A has degree n, where n is the size of A, what is the maximum possible number of roots I can have here? Well, by the fundamental theorem of algebra, I know that I have n roots. And if I am counting with multiplicity, and I've already said that I don't care whether or not the eigenvalues are complex or real, so I'm including complex numbers here as solutions or as roots of this polynomial, then by fundamental theorem of algebra, I know that any matrix has n eigenvalues counting with multiplicity, right? So fact A n by n has n eigenvalues counting with multiplicity. So, of course, counting with multiplicity means maybe the resulting, for instance, in the 2 by 2 case, maybe the resulting quadratic has a single real double root. We count that twice. Okay, you're very aware of how that goes. Any arguments about multiplicity? Okay, so lambda equals 1 and 5 are the eigenvalues of A. How do I go about finding eigenvectors before I go any further with other examples of eigenvalues? So this process is totally deterministic. I write out quadratic. Absolute worst case scenario, I use quadratic formula. I get answer, right? I find out what my eigenvalues are. I don't care if they're real or complex, so I'm happy regardless of what happens. And there we go. Lambda, I solve for these roots. I get my eigenvalues lambda, and I'm happy. So I'm almost done with what I want. I said that I am happy if I can compute the eigenvalues and associated eigenvectors. And so, question, how do I find eigenvectors associated to my eigenvalues? And the answer is the Cayley-Hamilton Theorem. So as I said before, this is not required. In fact, if you know how to solve for these anyway, then you don't have to do this at all. You can totally ignore what I'm going to say here. But if you don't know how to find eigenvectors, then here's how it goes. So this only applies for 2 by 2 matrices. So finding eigenvectors for 2 by 2 matrices. That's all I'm going to ask you to do on an exam. If you want to find eigenvectors for larger matrices, you would have to do it just the usual brute force way that you're taught in 240 or 461, where you solve some linear systems that result. It's not complicated. It's just slightly annoying because you have to revert back to solving linear systems, which can be kind of annoying. And so to avoid that entirely, I'm going to use Cayley-Hamilton Theorem. So what does the Cayley-Hamilton Theorem say? So Cayley-Hamilton Theorem says that a matrix, thought of properly as plugging it in a way that makes sense, it is that a matrix solves its own, or is a root of its own characteristic polynomial. Now, I'm using that word a little loosely because we're plugging in a matrix, not a thing here. So it says that if I plug A in to its characteristic polynomial, I get the zero vector. Don't strain your brain thinking about this too much. Don't even worry about this, okay? Which means that since P sub A of Z can be factored as Z minus lambda sub 1 in the first here, that's terrible. Let me rewrite this. So since P sub A of Z is equal to Z minus lambda sub 1 times Z minus lambda sub 2 for a 2 by 2 matrix, right? So this is for a 2 by 2. Then 0, that is the zero vector by Cayley-Hamilton, is P sub A of A, which is using this fact. This is A minus lambda sub 1 I times A minus lambda sub 2 I. Okay, which can be read in the following. So again, even these things you don't have to focus on too much. So what does this mean? So fact, this is what we're actually using. This is another 3-star fact. Okay, so what does this mean? So every non-zero column of A minus lambda 2I is an eigenvector associated to lambda sub 1. Why? Every non-zero column here is some vector that when I multiply on the on the left by A minus lambda sub 1I, I get 0. But that's exactly the condition for a vector to be an eigenvector associated to lambda sub 1. So every non-zero column of A minus lambda sub 2 of times I is an eigenvector associated to lambda sub 1. And similarly, every non-zero column of A minus lambda sub 1 I is an eigenvector associated to lambda sub 2. So this, when I say Cayley-Hamilton, really ignore all this part. What we really care about is what I have put in the box right here. Okay. All right. And so let's use this to go back to that example that I just did. So I did an example where my matrix A, I believe, was 3, 2, 2, 3. And we had previously seen that the eigenvalues were 1 and 5. Okay. So the eigenvalues were 1 and 5. So now I want to find eigenpairs. So I want to find all eigenpairs for A. So I want to find an eigenpair associated to the eigenvalue 1 and an eigenpair associated to the eigenvalue 5. Okay, so going back really quickly, what does Cayley-Hamilton tell me? Cayley-Hamilton tells me that if I want an eigenvector associated to lambda sub 1, I should look at any non-zero column of A minus lambda sub 2 I. And furthermore, if I want to find an eigenvector associated to lambda sub 2, I should look at any non-zero column of A minus lambda sub 1 of I. So recall that I is the identity matrix. In this case, it's 2 by 2. So I is 1, 0, 0, 1. So then let's look at lambda equals 1. Okay. So for lambda equals 1, if I want to find an associated eigenvector, I should look at A minus 5I. And I should look at the non-zero columns. So A minus 5I looks like what? So A is 3, 2, 2, 3 minus 5 times the identity matrix, which is 1, 0, 0, 1. So this is 3, 2, 2, 3 minus 5, 0, 0, 5. So this is, it's entry-wise. So the matrices have to be the exact same size, but once you have that, you just do any of these operations entry by entry. So this is 3 minus 5, so that's minus 2. And in the next entry, this is 2 minus 0, so that's 2. In the next, it's 2 minus 0, so that's 2. And lastly, this is 3 minus 5, so that's minus 2. Okay. So A minus 5I looks like that. I'm told that any non-zero column of A minus 5I will be an eigenvector associated to lambda equals 1. So I can choose any column. That might seem a little strange, but I'll talk about that in a second. So any non-zero column works. So an eigenpair is 1 minus 2, 2. So in this case, I will call this lambda sub 1, and this will be called V1, which is the eigenvector associated to lambda sub 1. Now, a couple of things you might notice. I said any non-zero column works, but clearly the column minus 2, 2 is different than the column 2, minus 2. So why would it work just as well if I had used this instead? Well, what's the relationship between this vector and this vector? Well, these two vectors are related just by multiplication by minus 1. And recall that way back, one of the first facts I said, it might have even been fact 1 when talking about these things, was that if you have an eigenpair of A, then lambda and alpha times V, where alpha was any scalar, is also an eigenpair. So considering this is also fine. In fact, if I wanted to make my life easier, what's another eigenpair I could have used here? What about this? Is this the same eigenpair as these two? Yes, it is. Why is it the same? Well, it's just like this eigenpair, except I've multiplied this vector by 1/2, which is allowed. I'm allowed to scale this eigenvector however I want to. So that works out perfectly fine. Okay. So let's do the other one. So let's do this for lambda equals 5. So for the lambda equals 5 eigenvalue, I want to look at a minus 1 times I, which is a minus I. So that's 3, 2, 2, 3, minus the identity 1, 0, 0, 1. And so that is 2, 2, 2, 2. And so 5, 2, 2 is an eigenpair for A. Another eigenpair would be 5, 1, 1, or 5, minus 3, minus 3. Any of those would work. Okay. So we want two eigenpairs. So we want to form exhaustive eigenpairs. That is, we want to find an eigenpair associated to every eigenvalue of lambda. So eigenpairs of A are, for this example, 1, 1 minus 1, and 5, 1, 1. And so by convention, I'll say this, if this is lambda 1, I'll call this V1. And if this is called lambda 2, I'll call this V2. Okay, so again, the proper way of thinking about this is, the way to read this off is 1 minus 1 is an eigenvector associated to the eigenvalue 1. 1, 1 is an eigenvector associated to the eigenvalue 5. Okay. A has eigenvalues 1 and 5. These are the eigenpairs. All right, so now I claimed that, and I'm going to do plenty more examples of this. We're going to do a ton of examples of this stuff. So I claimed that this was it, right? This was the main thing. This was like the main meat of this chapter. If you could do this, you're like 80% of the way to doing every problem. So then how do I use this? So question, how does finding eigenpairs of A help me to solve x prime equals ax? The answer to be seen, there is a recipe. That recipe is in terms entirely of the eigenpairs. Okay, this recipe is extremely reminiscent of the recipe for the homogeneous solution to a second order equation. Okay, so there's a recipe. This recipe is based entirely on finding the eigenpairs. So the eigenpairs are the things that specify this recipe, but we'll get into that next time. So let me go over. When's the final? I believe our last day of class is May 12th, which means that originally the final would have been scheduled for May 14th, which means that it would have been like graded 2-ish days later, 16th, all the grades be put in by the 17th or 18th. So what I'll say is I'll post it maybe like the 12th or so. Maybe I'll post it on like the last day of class, and then you'll have until the 17th or 18th to turn it in. Maybe a little bit sooner than that, because the TAs need some time to grade it, of course. So I'll post it on maybe the 12th, and we'll say that it'll be due like the 15th or so. Okay. Something like that. It will be in a similar format. It will be cumulative, and you will have a few days to do it. In terms of length, it'll be slightly longer than the one that you just took. I mean, it will be enough to have material from every section on the test. Yeah, it's obviously take home. How else am I going to do it? So yeah, I mean, unless you guys have a method of taking it telepathically or something. Uh, is this chapter hard? Is this chapter harder than chapter 2? I think this chapter is extremely far easier than chapters 1 and 2. But of course, I think a lot of the struggle with this chapter comes from students that maybe don't have the linear algebra background. So to them, it just seems like something completely like out of nowhere and just doesn't mesh with anything. But I promise you, if you get down how to find these eigenpairs, this chapter is extremely easy, in my opinion. And I should say this chapter is like, if you thought that the previous 2 chapters were formulaic, this is like formulaic to the max. There's absolutely like no thinking. Like if you just do the computations, you literally are just following the steps it's like a flow chart that's like completely deterministic. A review session or a live stream for the final exam. I will continue to do lectures, and I mean the last lecture I do will probably be just tidying up chapter 3 stuff. I guess in terms of review, I will at least have like a list to remind you, of what is important in each thing. So part of that last lecture, I will make a long list that you can have a look at. But other than that, that's it. What are we leaving out? Basically the stuff at the very end, and the other stuff we're leaving out is in class. I would have gone over more of the theory stuff at the beginning. So I'm just going to leave that out because it's not really going to add anything to the class at all. So I'm just getting you practically how to solve these. So actually, in terms of what we're leaving out, we're not leaving out a whole lot. Like I said, the very end of chapter 3 stuff will be left out, but apart from that, that's pretty much it. The main things in chapter 3 that are represented on the final exams from years past are the eigenmethod stuff, which is what we're doing now, the classification of phase portraits for linear systems, which is what we're going to do after this stuff, and that's pretty much it. The other stuff that's been on there in recent years, there hasn't been a whole lot of stuff from chapter 3 that isn't that stuff. So we're actually not leaving out too much. And the other thing, your second MATLAB project, which will be your last MATLAB project, I will post some point later, either later tonight or early tomorrow morning. So I will put out an announcement when I do that. You can just work solo. You can also work in groups. So if you work in groups, just specify that you have worked in a group and make sure that you've put your name on it. You should still restrict yourselves, even though everybody's remote. You should still restrict yourselves to working in groups. If you're gonna work in a group, you should restrict yourselves to working in groups with people that are in your section. And this is just so that TAs don't have to do a bunch of cross-sectional stuff checking with other TAs. It's made even harder by the fact that it's all remote. So so you can work totally solo if you want to and submit it. You can also work in groups. And submit in groups. Just make sure, and if you do that, you don't all have to submit it. You can just submit one per group. Just please make sure, obviously, everybody's name is on it so that everyone gets credit. And again, the project, if you're working in a group, only work in a group with people that are in your section. Or at least share your TA. But actually, no, I'm not even going to do that. So it has to be your section. Let's make it as easy on the TAs as possible. So anyway, that's the deal. So I'll see you all on Thursday. We'll continue on with this eigen method stuff. Your discussions tomorrow and upcoming GSS sections will be a bunch of linear algebra review, eigenvalues, eigenvector stuff. So anyway, see you all on Thursday.